So in this lecture, I want to show you the steps that I went to try to create a single component pressure temperature phase diagram. And I haven't seen this in a textbook before for, I think, good reason I've come to recognize. But for me, anytime that I open a textbook and it says, oh, well, here you do this, this, and this, and they show you a solution, I think, well, does that really work? So I thought I would try to create a pressure temperature phase diagram using, kind of order of magnitude correct numbers. And the first thing you think is well, okay, the books show you the constant pressure change in enthalpy and entropy. Most of the time they ignore the pressure part. And you think, well, maybe what I can do is have pressure versus temperature. And, you get something that does kind of like this, So you get solid, liquid, vapor. And you think, well, hey, this is P naught. What if I take my constant pressure equations and I modify the heat capacities? And that was my first approach. And it doesn't work, not to spoil the surprise, but let me show you how I went about this, what comes out, and then show you the next iteration, which does seem to work, and an implementation of this that I put into Mathematica. Okay, so we have G is equal to H minus TS. And what we want is we want to get G for each of the phases, solid, liquid, vapor, as a function of temperature and pressure. So we can wind up with something that does, I guess it's going to be negative here, right? It's going to be G versus T. I'm going to do, think about this for a second. It's going to do like that. Hang on, it's easier for me to think with the solid first. So if I've got a solid, it'll be a lower enthalpy and a lower curvature. So something like that. I have a liquid, which has a higher enthalpy because we know at 0 Kelvin, the free energy and the enthalpy have to be equal. So we have a higher enthalpy for the liquid and a higher curvature. And we know we have a higher curvature because the slope of the Gibbs free energy curve, this slope, is equal to minus S. And we know that the entropy for a liquid is higher than that of a solid. So the slope has to be steeper, and the enthalpy here has to be higher. And now the vapor has an even higher enthalpy and a higher slope. So it's going to do something like that, vapor, which means that you have melting point and a vaporization point. So this is how to think through these in terms of what's happening at 0 Kelvin and the slope of the curve. So we want to get those, which means we have to get the enthalpy and the entropy. And the way you get those is having the enthalpy at some known point plus delta H as a function of temperature and pressure. So I tried to create this using a minimum amount of data, right? When you're making up curves or you're making up problems for yourself, if you can minimize the amount of data, then you have the highest probability of having a self-consistent solution. And you don't, well, basically the error propagates in a way that is potentially self-canceling. So I said, okay, let's assume that my reference is 298 Kelvin, 1 atmosphere, and we'll say that the phase that is equilibrium is liquid. Okay, whoops. So that means the change in the enthalpy solid, liquid, vapor. The liquid, we'll do the easy one first, is the enthalpy at 298 of the liquid. And that's our reference. So, it's liquid, and H298 liquid has to be known. We also need an enthalpy at 298 liquid. And then we can integrate from 298 to the temperature. So this is going to be delta H is a function of temperature, right? Because it fits in there. Cp of the liquid dt. So we need the heat capacities. Liquid, solid, liquid, vapor. So we need 3 heat capacities. Okay. Thinking of the solid, well, because I wanted to use the liquid as my reference, then in the liquid phase, I'll integrate from 298 to the melting temperature of the liquid, dt. So basically, I am my vapor, liquid, solid. And if I have T melt, T vapor, and let's call this my temperature of interest, or whatever the function's temperature is. And I said that it's liquid at 298, which means this must be 298, has to be above the melting point. Okay. And for our liquid, I took liquid, solid, vapor. I took the reference, and then I integrated up to T melt, or so up to the T of interest. For the solid orange, I'm starting out in the liquid phase. I'm going to integrate to the melting temperature. I then transition to the solid curve, and then I trace up the solid curve to the temperature of interest. So that means I need the latent heat, and I'm taking the latent heat of solid to liquid and the latent heat of liquid to vapor. So here, because, man, I'm having a hard time with this, because I'm not going solid to liquid, but I'm doing liquid to vapor. That means that this has to be minus SL, because we're going down as opposed to going up. And now that I'm in the solid phase, I integrate from the melting temperature to the temperature T. And in a similar fashion for the vapor phase, I start out at the reference. Now I'm going to go up in the liquid till I get to the vaporization point, go up by SLV, and then back down until I get to the temperature of interest. So I'm looking for those 3 points on these 3 curves. So that means that this is going to be equal to H298 liquid plus the integral from 298 to TV CPL dt plus latent heat of liquid to vapor plus the integral from TV to T CPV dt. Okay, I've got those. And then the entropies that correspond to that in the same paths are delta S sol as a function of temperature is equal to S at 298 of the liquid plus the integral from 298 to the melting temperature, heat capacity of the liquid over temperature dt minus L S L over Tm. Again, negative sign there because we're going down. So that's the entropy of transition. And now that we're in the solid, we go from Tm to the temperature of interest, Cp of the solid over T dt. Delta S of the liquid, again, the easy one, is S at 298 of the liquid plus the integral from 298 to T CPL over T dt. And then delta S of the vapor, S at 298 of the liquid plus the integral from 298 to the vaporization of temperature CPL over T dt plus L over going from liquid to vapor over T of vaporization. Now in the vapor phase, we go from vaporization temperature to the temperature of interest, Cp of the vapor, T dt. Okay, great. Now we have those. We can substitute them in and get G sol G liquid and G vapor. And turns out when you do this, you get something that looks, well, just like this. You get exactly what you're looking for. Now, what that means is it means that at that constant pressure, we can determine the melting temperature and the vaporization point based on where these curves cross. Great. Well, the thinking was, and this is wrong thinking, was that if I had that point and that point, if I could simply go up and make these heat capacities all depend on the temperature and the pressure, and my approximation was that Cp is equal to A plus Bt plus Cp. I just gonna have them be linear with temperature and pressure, right? And I thought, okay, I'll put that in, and I'll get G versus T. I get curves, and they'll change as a function of pressure, which would let me, for example, mark out different pressures, fit a line, and have the phase diagram. Not so, because as you change or add that capacity, temperature and pressure dependent, what really happens is your curves do this. They may, well, that's a little bit of exaggerated, isn't it? They may do something like that and that. The curves definitely change shape. They definitely change shape as you add a temperature dependence to your constants, but the intersection never changes. And that's because all of these equations are coupled through the use of the melting temperature and the vaporization temperature. So if this were to work, which by the way, it doesn't, you would need to have the temperature of melting and temperature of vaporization as a function of pressure and temperature. And if you had that, you'd have no need for the curves anyhow, because you would just plot them. That doesn't work. And we derived in class the, I don't know if we derived it, but we saw in class the change in the enthalpy and the change in the entropy as a function of pressure holding temperature constant. And we know that they should be delta H changing from pressure 1 to pressure 2 is V1 minus alpha T dP, and delta S is equal to the integral of minus alpha V dP from pressure 1 to pressure 2. Okay, so what we really need to do is we need to take this and put it here, here, and here. And the same thing with this, putting it here, here, and here. And I did that, and I'll show you that in the implementation in a second. But other points of interest and points that I think they help explain why textbooks don't show this. And those 2 points are one, and this is a minor point, what's the temperature in there? Well, that fortunately can be any that matches a reasonable path. And what I mean by that is I mean that we know that enthalpy is a function of temperature and pressure. So if I have some curve, it's now a surface, and I'm at some temperature and pressure, T1, P1, and I transition to T2, P2, I could change the temperature, I could change the pressure. Man, my hands. Change the pressure and then change the temperature. Or I could change the temperature and then change the pressure. Or I could pick some other completely random path, and it doesn't matter. The output has to be path independent. So as a matter of convenience, I've decided that I'm going to change the pressure first, holding the temperature constant. So that's going to be, T1, but it doesn't have to be. And I went through and I checked this to make sure that the numbers work. And indeed, our enthalpies are path independent, which is great. The second point that I think also is kind of interesting here is that you now have a volume in here. Well, again, our textbooks, when we start talking about these things, we have PV equals nRT, and we go from there. But that doesn't really work, at least not if we want a reasonable phase diagram, because we know that in the ideal case, then alpha, the thermal coefficient of expansion, is 1 over temperature, which means that this whole thing goes away and there's no enthalpy contribution. And we don't want that. It also doesn't work because, well, we don't have a gas, we have solids, and we have liquids. So what I thought I would do in the process of, making an approximation was to incorporate the compressibility. And we have that the compressibility is equal to minus 1 over the volume dV by dP, which means dP is equal to minus 1 over beta 1 over V dV, which gives us, P is equal to minus 1 over beta natural log V is equal to natural log V minus 1 over beta. And we wind up with V as a function of P is equal to X of P minus beta, which means a volume versus pressure curve has this functional form. And that makes sense, right? Because as you increase the pressure, you're squishing the volume, right? So we're decreasing. And what also is telling us is that as we get to higher and higher pressures, the rate that the volume decreases, right? Because matter is getting compressed. So that shape works. And a problem here is that beta compressibility is only for fluids, liquids, and vapors. But the good news is that solids don't have compressibility, but they have a bulk modulus. We'll try spelling that again. And the bulk modulus, K, is equal to minus V dP dV, which means we should have a very similar, as in, this exact same shape for a solid. So we can treat this as a reasonable expression for the volume as a function of pressure. So let me show you how I implemented this. And I think at least for me, for doing a lot of theory work, I'm a very concrete person. I have to actually see how it works out. And I think that you'll see here how a person would go about implementing this, and more importantly, how he'd go about fixing it to making it a better model. So I started out putting in physical constants, And I usually just keep those at the top of my code, and I'll turn them on and off depending on if I want to work numerically or I want to work analytically. So these are the heat capacities, and I put S, L, and V to specify if it's a solid, liquid, or vapor. And these are reasonable if you want to add pressure and temperature dependence. So you have, Cp is equal to A plus Bt plus Cp. That is going to be, on the order of 50, and that is joule per mole K. B is going to be ranging kind of between 0.1 to 1. And that's going to be, whatever, joule per mole K squared. And C is going to be negative. So C is going to range anywhere from minus 0.01 to minus 0.1. I guess that's joule per mole per Kelvin per atmosphere. So that's joule per mole KATM. But you don't need that. Well, you do, but we'll get to that later. You find that the thermal coefficient of expansions, typically going from a solid to a liquid to a vapor, you've got about 1 order of magnitude difference. So I just put in, 10, 100, and 1,000. This, I made that a little bit on the large side. This is typically around 1 times 10 to the minus 6. I needed to put that in to have a little more of a shift, and you'll see later. These values become problematic when you start making a plot, but it has the right functional form. We just need a better expression for this. And so these are units of 1 over temperature, 1 over Kelvin. And again, going from solid to liquid to vapor, you've got about a 1 order of magnitude change in the compressibility. And this is units of 1 over atmosphere. Latent heats, again, about 1 order of magnitude different between them. Solid to liquid seems to range anywhere from 1,000 to 10,000, and vapor anywhere from 10,000 to 100,000. And then your enthalpy and entropies of formation of a liquid. I picked this a little bit on the small side. The H at 298 typically ranges from minus 10,000 to minus, well, it can go up to 1,000,000, but I would say really around 100,000. So I picked a little on the small side, and again, it's because I was trying to see if I could force these curves to interact more. And if you decrease the latent heat, the enthalpy of formation, you do see a little stronger interaction. But and this ranges anywhere from 10 to 100 joule per mole K. And these are reasonable melting and vaporization temperatures. And I cleverly closed my curves before I printed this. Let me open a new document. Okay, sorry. Here are the enthalpy curves. So in these, that is our V is a function of pressure. I substituted into my function the analytical solution to the integrals here and here. And the reason I did that is because the integral turns out the same every time. And rather than have the software perform the integral, whether it's numerical or analytical, if you just copy and paste them in, they go faster. So if you're on a enthalpy curve and you're at some temperature T1 and P1, maybe I should draw this in 3D, huh? H, temperature, pressure. If I'm at T1, P1, and I transition, and I'm transitioning by keeping the temperature constant, changing the pressure to T1, P2, and then T2, P2, this difference in the enthalpy is the temperature dependent part, Cp times delta T. And again, we're treating Cp as a constant. If it wasn't, it would have to be put into the integral correctly. And this is our V is a function of P1 minus alpha T star. And this function, delta H path, and this is the path on there's no change in the phase. This is just a constant phase. I put in temperature 1, temperature 2, pressure 1, pressure 2, T star. That's the temperature that goes into the pressure change in the enthalpy, and then heat capacity, thermal coefficient of expansion, and our compressibility. So implementing this, you can see the liquid, you've got the reference, and then the change from 298 to the temperature of interest, 1 atm to the pressure of interest, holding that as T star in the change in pressure, and then to specify that this is the path on the liquid surface, I've got L, L, and L, which I specified at the top of the sheet. Going to the solid, I start in the liquid phase with the reference enthalpy. I change the liquid phase up from 298 to the melting temperature, holding pressure constant and using 298 as my temperature of interest, or my, the temperature I'm holding using for the pressure change. I then have the latent heat, and now in the solid, because I used S's, I'm integrating along the path from T melt, the temperature, pressure 1 to the new pressure. And note here that, whoops, there's no pressure change here because we need the latent heat at the 1 atmosphere, because that's the value we know. Yeah. We know this is at T melt, P equals 1 atm. And then the vapor, 298 liquid, the liquid going from 298 to the vapor temperature, transition from liquid to vapor, and then in the vapor phase, transition from the vapor temperature to the temperature of interest and the pressure of interest. And if you now plot these, you get the vapor. So the vapor is in red. And I have the vapor at 1 ATM, 10 ATM, and 20, 20 atmospheres. And then I made that red dashed and red dotted. So you can see a little bit of change there. I've got black for the solid. So this is solid, vapor, and liquid. I've done the same for the entropy as I did for the enthalpy. Whoop. Same paths. And this is our entropy curves, which means we can come down and look at our Gibbs free energy. So the Gibbs free energy of the solid is the enthalpy of the solid minus T S of the solid, etc. And here's what we've got. So this is our vapor. This is our liquid. And this is our solid. And zooming in here, that is our melting temperature, and that is our vaporization temperature. And you can see the enthalpies and the entropy, the enthalpies and the free energies match at 0. And this is nice. This does what it should do. So let's zoom in. This is the temperature. And I've plotted here the solid. I'm doing a solid in black. So the solids at 3 different pressures, 1, 10, and 100 atmospheres. And the liquids in blue, again at 1, 10, and 100 atmospheres. And you can see how changing the pressure results in shifts in the melting point. We can do the same thing for this is vaporization in red, the vapor in red, and the liquid in blue. So again, you get TV is a function of pressure. So where did we get the phase diagrams? Well, we get the phase diagrams by setting the Gibbs free energy curves equal, right? To give you your melting point and your vaporization point. So here I numerically solved setting the liquid and vapor equal to each other. And I call this the liquid vapor line. And I did this for various pressures ranging from 0 or 1 to 100. And you wind up with, and this is a little bit different from what you see normally because this is temperature versus pressure. So this means translating that into pressure, temperature. This means that at, let's call this 1 atm for 50, as you increase the pressure, you decrease the temperature. So this curve is doing that. And this is the liquid vapor. Okay. And then here I've got the liquid solid line. So this one says that it's at 350. This says that as I increase the pressure, I increase the temperature. So that gives me something that does this. And here's where things start getting a little funky here because the solid vapor line, well, the solid vapor line is going to have to be at considerably higher pressures. And you'll see here in a second where this starts breaking down. So what I did next was I took the temperature pressure and I fit a linear curve, right? So for each of these, LV and liquid solid and solid vapor. And this is where things start breaking down. Again, this is temperature versus pressure. These do not come to a single point. And that's because our physical constants are not constant. Which means that I really, if I want to do this correct, and again, this is why they don't show these in textbooks, because if you want to do this correct, you're going to have to go back up here to the top and get these physical constants to have significance. So I think that what I've shown you here is the right path to get things going using compressibilities or bulk modulus. But to really get curves that are meaningful, the heat capacities, thermal coefficient expansions, and your compressibility or bulk modulus are going to have a temperature and pressure dependence. So I think, if I'm teaching this class again in 2 years from now, I will have data for this prior to teaching so that I can derive a real phase diagram. And again, this also, I think, points out the significance of all of the people who spend their lives measuring thermophysical properties. It's not an easy thing to do, but it's essential for all of us that want to have phase diagrams that work. So I will pass this out to you guys so you can work with the Mathematica document if you can. I think they have access to Mathematica in the physics department. I don't know how to get access to that for you. Maybe there's labs there that you can use that are open during the day. But you can certainly mimic these yourselves.